Weierstrass M-Test is one of the most elegant pieces of mathematics that gets underappreciated and underemphasized in standard courses. One of the reasons I believe is that there isn't enough context that many students share, so there isn't room for really expanding on what is happening behind this theorem. And number two, its proof is amazingly simple, which gives the impression that it's not that deep. I hope this lecture will convince you otherwise. Let's see the first times you kind of visit this amazing theorem in undergraduate courses. The first one is absolute convergence. You have some sequence of numbers, and in their summation, some of them have a minus sign behind them. And this absolute convergence is just to get rid of those annoying minuses and guarantee that if the absolute values converge, then no matter how you assign these minuses, that signed series will also converge. Next step, the deeper version that you see, which is probably the standard meaning of the M-test, the one that is also on Wikipedia, is that if you have a sequence of functions with some norm, usually the supremum norm, the norm that guarantees that the limits will remain continuous. And these norms happen to be bounded by some numbers, mn, and these summation of mn converge, then the function series also converges. But here it's deeper because now this convergence is more than just convergence of numbers. As functions, they converge. That means in the norm specified. So what is the true context? What is the setting? What do you need for this theorem? You need a vector space because you talk about series and you need to be able to add things, right? So first thing plus the second thing, and then for series, hopefully you add many more and then take limit. Wait a second, we said limit, so that means there should be a notion of distance, and the most convenient one is when this distance comes from a norm. So it's a normed vector space. You can assign a number, a non-negative number, to every element of this space. And the next thing you need is that this space is complete, so that Cauchy sequences have guaranteed limits, and that means the space is a Banach space. So you need these three elements to talk about what's happening here. Now, examples before, so that you can appreciate this. This can be Rn, any Rn, and then you talk about adding vectors, they have a norm and so on. Even R2 is very interesting because you have complex numbers. You talk about the summation of 1 plus z plus 2 times z squared plus 3 times z to the 3 and so on. And their convergence as complex numbers is a bit different than their convergence if this z was a real number, because now if z is here, z squared not only has different size but also different angle. So maybe z squared is here, and then to the cube maybe is here. You see that if you want to add these vectors or complex numbers and have a convergence, you have to not only worry about the length of these vectors, which would be the case if this was just real numbers, but you also need to worry about the change in the directions. And if this is a infinite dimensional Hilbert space, then there are infinite directions you can go to. So Rn, Hilbert space, what else? Space of matrices, say x equal k by k matrices with some norm. Space of functions, which is the one in the previous example. Space of, say, continuous functions or just functions, and many more. So what does the Weierstrass theorem says? And here is the true beauty and elegance of it. It says that suppose vi are in your vector space, normed vector space. If you take norm of these objects in your space and you add them and it converges, which is equivalent to just remaining bounded, then this summation of vi itself converges. But these two words have extremely different meanings. Here you're talking about a convergence of some stupid positive numbers, just as boring as it gets. And here we are talking about convergence of objects in your in your vector space. And that can have very strong consequences. Like if you have a sequence of functions, you're claiming that the summation converges to a function. If you are talking about complex numbers, that means all these angle changing stuff just balances out, and at the end you get a limit. If you are in Rn, the same, and so on. This just is so beautiful because you conclude a very meaningful convergence, a convergence that is really consequential from a boring convergence of some positive numbers. That says, it's saying that ignore all the angles, all the directions. Even if you are in an infinite dimensional space, just forget that these are objects pointing in infinitely possible many directions. Take norm, reduce everything just to R1, and add these values. And if they converge, you're guaranteed that the summation of vectors, objects, will converge. The proof of this, if you check it, if you don't remember it, is so simple. It's just proving that these form a Cauchy sequence, and that is by just looking at the tail. The tail is dominated by this, so it's triangle inequality. The tail of these summations are in norm bounded by this tail, but this tail goes to 0 because it's convergent by assumption. Therefore, you get a Cauchy sequence, and that's where you need this assumption of being complete in Banach to guarantee that you have a limit. Now let's see some applications in our context. For instance, if you look at this sum, so 1 plus x to the 2 factorial plus x to the 3 factorial, and so on. So this is supposed to be e to the x, right? But in what sense? You can talk about a fixed value of x and think of this as happening in R1, but the deeper viewpoint, which is why they introduced the M-test in these books, is that now you, instead of this, you forget that and you think of each of these as a function. So this is function f2, this is function f3, and then if you restrict all of them to some interval in R, right? If you restrict them to some AB, then each of these functions, their supremum norm is bounded by some number to the power n. It grows like a power, which is like the maximum of absolute value of a and b. And this, you call it as mn. Wait a second, so that is the powers growing, so there's n factorial here, very importantly. And now we see that summation of mn, now this is a summation of not functions, just numbers, is bounded by or less than e to the e to the c that appears here. Anyway, it's bounded. So from this you conclude that as functions, this 1 plus x to the 2 factorial and so on converges to a function. And because these are continuous, I mean, you're talking about L infinity norms, so the limit function will also be continuous just from being in your space and the way things are set up. And this function, now you can give a name because now you know it exists, so it's been called the exponential function, written in this funny way. Another immediate thing is that if you just change all of these to z, you can see that if you're focused on some bounded disk, there is a bound on this z, which is just the radius of that. And for the same, so let's say this is c actually, the radius, then you get these same bounds and then you get these same convergence. So it doesn't matter if your x's were real or complex. So from the same theory, from the same viewpoint, you also prove that exponential e to the z exists. You can apply this to now sine, cosine, whatever. Okay, but still I'm repeating what you have seen. Let's look at the other contexts. For example, the k by k matrices. You have definitely heard about exponential of a matrix. I'm sure that's not new to you. But no one really defines it properly, I believe. What they say is that you have identity. This is a square matrix, so plus I plus a to the 2 factorial plus a to the 3 factorial, and so on. But wait a second, these are not just simple numbers, these are matrices. How am I guaranteed that these converge to some final matrix? Then I can call it e to the a. So what guarantees this? Here the answer that they don't give you is that the space of matrices comes with various norms, and we need some norm with which this space of matrices becomes complete, and a norm that satisfies that norm of a matrix to the power n is less than the norm of a, then to the power n. I hope you immediately see the difference here. For example, this would follow if you had a norm that just it has this inequality for the product of matrices. So product of A times product of B. If you take A equal B, and by induction you get that. I'm not sure if there is a norm that does not necessarily satisfy this, but it still satisfies that. That can be a good question actually. But anyway, if you have a norm satisfying this, then you get from above that that the norm of these quantities, if you put norm on these, norm of this, norm of that, so if you get that, then this becomes norm of the identity matrix. It's some number, and then it gets plus norm of A, okay, plus norm of A to the power 2 from our inequality divided by 2 factorial, then norm of A to the power 3 factorial, and so on. And now we're talking about summation of real numbers, and if you assume this is 1, then this becomes actually equal to e to this number. We're talking about numbers, no matrices here. And therefore you see that the norms converge, and from this you conclude that the vectors also converge to a matrix. Also, it's easy to see that the norm you get for the number you get from summation of norms always bounds the norm of the limit. So whatever this becomes, which is the limit of the vectors, will have a norm less than this number, which happens to be e to that. So you have seen this inequality probably also, but now it has a very different meaning, and also a proof that you understand. So space of matrices, we saw example, space of functions with complex numbers, it was interesting, and so on. Now let me give you the most probably deepest example. So here, lemma, there is a Sobolev function on say R2, you can do Rn, that is essentially unbounded on every open set. Like it's truly it has infinity peaks everywhere. So how do you prove it? Using our Weierstrass thing. So first, you can take x to some power with the right choice of a. I am not being super precise here. For example, I don't say what w1p or something. I don't even fix p, but with every p you can probably do this. So with the right choice of alpha, maybe negative, such that, let's call this u1 of x, such that u1 is in the Sobolev class that we wanted, and truncate. Okay, take this and then truncate. So you can have your first function that has a blow up at 0. So it's also symmetric. So it's just like this. It blows up at 0. But it is, and then you can truncate, maybe make it just 0 away from there. So u1 is a Sobolev function, and with that. Then you do what? So for fixed, say z1 in the plane, the function, maybe let me call it z2. z1 b0. The function u2 at x given by u1 x minus z2. So I just shift this blue thing to a new center like this. Is also Sobolev, but also I can put I can divide by say 2. It doesn't take away being Sobolev, and it doesn't take away having this pull. Now I can do this for many choices of them. Okay. Next, what do? Let z1, z2 as above, but add many, be a countable dense subset of R2. Let u n of x be shift u1 to z n and divide by 1 over 2 to the n. Then the Sobolev norms are bounded by the Sobolev norm of that. So if you take the Sobolev norm of this thing, w1p, will be bounded by Sobolev norm of u1, 2 to the n. Therefore, summation of these norms, n equal 1 to infinity, converges as real numbers. So summation of un as functions on R2 converges in w1p. So the end result becomes a function. And these functions pointwise are always positive. So you see that each one has this infinite peak at Zn, so it follows that at every Zn you have a peak of infinite, but these Zn's are everywhere, they're dense, so it's even difficult to draw this function. So you get this picture, but everywhere, at every point of a dense subset, you get one of these. The reason it remains Sobolev is just crazy. It follows from this. You really don't want to do integration by parts for this summation, but the theory guarantees that it is a well-defined Sobolev function because, well, Sobolev spaces are complete, maybe the only reason we defined them in the first place, and the norm behaves the right way, and this, you see, it's an amazing application, I believe, of this Weierstrass M-Test thing. The beauty and elegance is that it just applies everywhere. As soon as you have the right context, you get it. A vector space, a norm with which it is complete. Done. Here we had Sobolev space. We had a bunch of functions we fixed by our hands in such a way that the norms converge. That was it. So I hope this brings some new appreciation for this theory and maybe motivates you to look at its proof once more, that how such a useful and beautiful theorem can have such a nice and simple proof. But that shouldn't take away from its elegance. Actually, some very deep results in math are simple to prove. If you have any questions, let me know. If you want to see me explain any other concept from standard textbooks in a deeper kind of way, in a way that I look at after these years, let me know in the comments and I'll be happy to make lectures about them. Thank you.